So, alright guys, this will be the first video about the Frank Hertz experiment. Here we will discuss the theory of the experiment itself. And then in a later video we'll discuss the apparatus and how to set up the experiment. Okay, and the data you should get. So, Frank's Hertz experiment. So this experiment was named after James Frank and Gustav Hertz. This experiment demonstrated the existence of excited states in mercury atoms, and in doing so, it helped support the Bohr model, for which they obtained the Nobel Prize in 1925. So before we move on to discuss the theory of the Frank Hertz experiment, let's talk about a little bit about what is the Bohr model. So if you look at here, this picture is not the best, but you can see here the Bohr model basically states that we have a dense compact nucleus that is positively charged, and then we have these electrons that are orbiting around what these are called stable orbits, and where they're these stable orbits, they do not radiate. So if you remember from mechanics, anything that goes in a circular path is accelerating towards the center. Well, here the model states that even though they're in a circular motion, they're not radiating energy. So they call those stable orbits. Now, the stationary orbits do not happen at just any random distances. As you can see, I could draw more of the orbits, but there's a spacing mandated by the following equation, by the following condition. So your distances, the distance at which you can have a stable orbit, are mandated by the equation you see here. So we need to have the angular momentum of the electron equals to integer multiples of the h bar constant. And if you remember, h bar is just simply h over 2 pi. Second, and then third point we talk about is the electrons. The electrons can only jump from one energy to another, from one stable orbit to another stable orbit, by absorbing or emitting radiation with a frequency that's determined by the energy difference between the levels. So this orbit corresponds to one energy level, then this corresponds to other energy level. If the electron was to absorb a photon, it jumps from this to this energy state. It spends a small amount of time there, because the electrons now like to be in its lowest energy state. Then it's gonna quickly fall back onto the original energy state, and in doing so, it will emit that same energy that it absorbed. So that's what you see on that equation over there. So you have that the energy difference, it's E2 minus E1, that's equal to HF. Okay, so this frequency of light has to match the energy difference between those two energy states, otherwise there's no transition between the energy levels. Okay, so how does this help us understand the Frank Hertz experiment? Okay, so let me erase this. Okay, and let me take where's the drawing? Now let's look at what the Frank Hertz experiment, the theory behind it. Okay, so we have here a very simple diagram of the experiment. So bear with me while I draw it. Okay. Okay, so what you see here is a simple diagram. So what we have here is a tube that is contained, let's say, mercury. It's a very low pressure gas. There's low pressure in this bulb, and you contain mercury gas here. You have this guy, which is a filament, and it's a cathode, which is a plate we're gonna keep at a potential, negative potential. So we say cathode, and then this is gonna be the anode, and then we call this guy the collecting plate, collector plate. Okay, so what's going on here? Okay, so you have this filament, which its purpose is to heat this cathode, and as it heats it up, it releases electrons. And then there's a potential difference between these two guys. And then here we can call it B collector. There's a B cathode and B anode. The potential difference between the B anode is higher. The potential at B anode is higher than the potential at the cathode. And so the electrons are being accelerated from the cathode to the anode. So while they travel in here, they still see there's still the mercury gas going on. It's still there. So they're gonna meet it. So they can collide with it as they pass through the tube. And so once they reach the anode, if they have enough energy, they can reach into the collector, and then be read as a current here. Okay, and then that produces a retarding voltage. This is going to be the accelerating voltage. Okay, so if we were to plot the current, so we could plot the accelerating voltage here. In volts, and then let's say the current there. From Ohm's law, we could expect that we're gonna get something like, before we did voltage, right? And then current, you would expect a linear relationship. Here we do the opposite. We plot accelerating voltage on the x, and then current on the y. But what you actually see is something that goes like this. And then I could keep going. So so this is more or less the idea. So what's going on here? So if you see accelerated voltage is increasing, so I'm just sending the electrons faster and faster towards the anode and then the collector plate. And if I accelerate more, I get a higher current. But then I get this trend here, this pattern. So what's happening? So as I mentioned, those electrons that are being accelerated here, they meet the mercury atoms and tend to collide as they will make their way towards the anode. And then the collector, and maybe might reach the collector plate. But as we said before, the Bohr model has a quantized energy. The states that the atom has a quantized energy states. So there's going to be an energy, a voltage at which the electrons acquire enough energy, so as they collide, inelastically with the electrons from the mercury and then tend to excite them to reach a higher energy. So what you see here is we're having, as the electrons are accelerating with increasing voltage, they have elastic collisions, so they're bouncing off each other with the mercury atoms. They reach that particular energy of the first excited state, so then they can transfer all of their energy to that mercury atom, and so mercury electron, and so they excite one mercury atom. After doing so, they're still in the potential difference in the electric field between the cathode and the anode, and so they get reaccelerated to reach the state where they can excite a second mercury atom. And if you were to plot this happens, these peaks are evenly spaced. So the energy differences, or the voltage, is evenly spaced. So, as you can see, these guys happen only at distinct energy differences and distinct positions in voltage. So that helps to support the idea that Bohr models quantized energy states are indeed a valid model for the atom. Okay, so in the next video we'll talk about the experimental setup. I hope the explanation was clear, and yeah, we'll now get to the second video.